Hi everyone, and welcome to Module 1, Lesson 3's live video notes. This lesson is going to go over a couple of things. Density, which I know you've done before, so it shouldn't be that hard. Percent error, which is going to be new to you, but it's a very simple equation. Temperature conversions, which I'm going to give you the equations, you just have to plug them in. And graphing, which I'm very briefly going to go over because I know everybody knows how to graph. So we'll start with density. Calculating density, very simple. Density is mass over volume, right? There's this little triangle thing that you can do that will help you. It's called the DMV triangle. And basically, if you cover up what you want, it tells you how to solve it. So if I want density, you cover it up, it's mass over volume. If I want mass, it's density times volume. If I want volume, it's mass over density. Or you can simply rearrange this equation to get the thing that you want. So what's the density of this block that's right here? So we know density is mass over volume. I don't have a volume, but I do have a length, a width, and a height, and we know that length times width times height equals volume. And we, of course, want to use our sig figs because we totally know how to use those now when we're doing calculations. So 5.2 centimeters times 17.4 centimeters times 8.7 centimeters with sig figs. So this is 2 sig figs, 3 sig figs, 2 sig figs. I need 2 sig figs in my answer, so it's 770, and my unit centimeters cubed. A cubic thing is a volume. So simply to calculate the density, 706.63 grams divided by, what is that, 770 centimeters cubed. Just put that in your calculator. We're doing division, so we want the least number of totals. So again, I need 2 sig figs in my answer, 0.92 grams per cubic centimeter. And just an FYI, 1 cubic centimeter is 1 milliliter. So if that ever comes up, you don't have to worry about, I don't know what a cubic centimeter is. It's the same thing as a milliliter. There will be an online virtual lab thing for you to do with density, so it'll give you extra practice. That's it for the notes. Now we're going to look at percent error. It's just a calculation. So percent error basically tells you how wrong are you. So if you went through module 1 lesson 1, we talked about accuracy and precision, and this comes from that. So the woman from those ones weighs herself on a scale, and we know her true weight is 130 pounds, but the scale reads 125. What is the percent error? Okay. Percent error is equal to the absolute value of the measured minus the accepted divided by the accepted, and then you multiply it by 100 to make it a percentage. We need an absolute value because your percentage can't be negative. The measured value, for this case, the scale reads, so that would be my measured. And then the accepted would be 130, because that's what she actually is. Accepted, or what you could say actual. Okay, you might see actual measured minus actual, or it could be actual minus measured. Again, absolute value does not matter. It's just important that the accepted value is on the bottom, and then you multiply it by 100. So percent error equals the absolute value of 130 minus 125 divided by the accepted, which was 130, multiplied by 100. If you were to do your sig figs, 130 minus 125 gives me 5. 5 has 1 sig fig divided by 130. I need 1 sig fig, and so you're 4% off, which is not that terrible. Anything under 10 is going to be good for a percent error for an actual lab that you're doing. And that's it for percent error. Pretty simple. And then we've got some temperature conversions. So when we talk in the scientific field, what temperature do we typically use? We use degrees Celsius. Less common, we use Kelvin. but typically it's going to be degrees Celsius. And so here are the conversions. Kelvin to Celsius, Kelvin equals degrees Celsius plus 273. This one we're going to use a lot later on in the year. And then the conversions between Celsius and Fahrenheit are given there. No need to memorize those. As long as you know how to use them, that's fine. I'm going to show you a couple of them, and I will write all the answers out, but you can do them yourself because it's merely algebra at this point. So we want to go 32 degrees Fahrenheit to degrees Celsius. So I'm going to use temperature in Celsius is equal to 32 minus 32 times 5/9, which of course is 0 degrees Celsius. We know that one. Kelvin to Celsius, okay? So I know 98, I'm doing the one that's circled, Kelvin is equal to degrees Celsius plus 273. In order to do that, I'm going to take away 273 from both sides. And so my answer is going to be negative 175 degrees Celsius. Okay, I'll let you do 3 and 4 yourself. For 4, there is no way to go from Kelvin to Fahrenheit. So what you have to do is you have to go to Kelvin to Celsius, degrees Celsius to degrees Fahrenheit. I'm also going to let you do 5 yourself. I'm going to come back and write in the answers here. Just note the human body typically 98.6 degrees Fahrenheit. Go ahead and turn that into Celsius. The answers, you should get 346.1 Kelvin, negative 62 degrees Celsius. Oh no, that's the Celsius one. It should be negative, well, and then the final answer would be negative 80 degrees Fahrenheit. And then the last one is 37 degrees Celsius. Okay. So go ahead, pause the video, try to do those problems. They're not that difficult. These should be pretty short notes for this lesson. And then finally, graphing. I'm not going to actually graph for you. The graphs I have done, and they are in the completed notes on the presentation page. So make sure you go ahead and look at that. But let's talk about things that you need for a graph. So let's look at this data table here. What are they asking? So basically, what they're doing is how long does it take to dissolve salt in water? That's basically the question they're answering or asking. But there is something that's wrong with this data. There are too many things changing. There are too many variables. For a good science question, we can only have one thing changing. Okay. So we would either need to keep the temperature of the, well, if we are trying to figure out how long does it take to dissolve salt in water, we either need to keep this all the same or this all the same. My instinct would be to keep this the same, and the temperature is what changes. So now we have independent and dependent variables. The independent variable is the thing that's controlled by the scientist. So if you think about this setup, what the scientist would be doing, turning up or down the Bunsen burner, turning up or down the hot plate. So the thing that the scientist is controlling would be the temperature. Now the dependent variable depends upon the independent variable, and the dependent would be the time to dissolve. So the next slide here is going to be just a practice problem for you to do. So a scientist prepared several water baths at different temperatures, and a balloon is attached to the bottom of the water bath, and the volume of the balloon was recorded. Here is the data from the experiment. There it is. Important to note, the independent goes on the X, the dependent is on the Y. So in this case, the volume of the balloon depends on the temperature. So if you print these out, this is a place for you to draw your graph, okay? But let's talk about what we need to make sure we include in our graph. So we're going to have a title. we're going to have to label the axes. And we have to include our units. Okay. We want a good scale. So that basically means every tick mark that I use on my graph has to be the same thing. So if this is 0, for mine, I started with 24 and I went up by 4. So this is 28, 32, 36, and so on and so on. If I labeled this, this would be temperature in degrees Celsius. This would be volume. And again, that's in milliliters. And my scale for this, I started here, it was 100. And I went up by, well, each one technically is 1. But I don't show every one because there's just not enough space. Okay. So that's what we mean by a good scale. You need to plot the points. And then we want a best fit line. Okay. So go ahead. That's the things that we need. I want you to stop here and graph that data, okay? If you want to, the completed notes are given to you so you can just see what the graph looks like. And then you can see that the relationship, even if you just look at the data table, it's going to be linear. What would the equation for the best fit line look like? Well, it's going to be y equals mx plus b. We know m is the slope, b is the y-intercept. To find the slope, we're going to do y2 minus y1 over x2 minus x1. So what you do when you have your graph, let's say this is what it looks like, okay? And there's a point here and a point here. These are not the actual points. Please look. What you do is you take these points that are on there, and then this would be x1 comma y1. This is x2 comma y2. And then you would do that math, y2 minus y1. The 2 points that I thought went through the best fit line the best, so you draw your best fit line and you pick 2 points that go through them. I calculated my slope to be, which is what it's asking for this next question, 0.31. All of the slopes are going to be relatively similar. When you hand draw it, there's going to be some estimating that you do. So keep that in mind. You could go ahead and put this into your calculator and you could graph it that way and you could actually get the best fit line perfectly. But if you don't have your calculator as an option, you should be able to graph this and get that information. So my y equals 0.31x. Now for my y-intercept, what you do is you would just continue on and draw your line. It's called extrapolate. Draw the line until it hits the y-axis and plug in what you got. So here it's a little different because again, this is just a graph I drew. I just drew a line. But what I actually got was about 98.5. And so that would be my best fit line. Again, I'm going to put some more videos up if you have questions about graphing and doing a best fit line and getting that information. Also, please ask those questions. There will be time after to ask anything. So as always, you can just ask those questions later. Now, if you wanted to calculate the volume of the air in a balloon at 100 degrees Celsius, that's my x. So we said temperature was my x. Okay, so we want to plug in x for 100 into this equation and solve for y, and that will give me a volume. And that will give me 129.5 milliliters. So that would be the volume of air in a balloon if the water was 100 degrees Celsius. Now the last question, I'm only going to give you a hint to guide you. It says plot the data and determine the density of the sample. You can determine the density of a sample when you plot mass versus volume, and the slope is the density. So all we have to do is the slope here. So slope, which we know is rise over run, is y2 minus y1 over x2 minus x1. Now, if density is mass over volume, that means the mass is the y, the volume is the x, okay? That's what you got to do in order to determine that, okay? So I want you to go ahead, graph that, okay? Again, the answers, my graph, are on the completed notes for you to look at. I don't think it's beneficial for me to sit here and for you to watch me graph. It's not important. So graph it, best fit line, 2 points that go through that line, that slope that you calculate will be the density. Now the density that I got was 11 grams per milliliter, approximately. Again, since we hand draw it, everybody's is going to be a little bit different, but it should all be relatively the same. Okay? That's it for the notes for this lesson. Please, 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 if you have any questions, there are so many ways to ask them. So please do that. All right. I will see you in the next video.